Okay. Okay, so combinatorial games, as I said, they're played between two players who alternate and take turns to move, and there's no luck involved, so no gambling, and the games always end with either one person winning or the game resulting in a draw. So examples include like tic-tac-toe and chess. So the fundamental theorem of combinatorial games. So because like the game is not luck based, right? So there's always going to be a strategy for both players. So what this means is there's either always going to be a winning strategy or both of them can force a draw. So oftentimes in Math Olympiad questions, they'll often just give you a game and they'll just ask you like, okay, which person has the winning strategy and like prove it. So I guess we'll go over a few examples first. If you have anything else to say, Chris. Okay, we'll just keep going.
I don't have anything else to say. You can
All
go
right,
on.
so the first example. In the game of double chess, the rules of chess are changed so that white and black alternately make two legal moves at a time. Show that black does not have a winning strategy. So I'll give you guys like a few minutes to think about this.
All right, I think I'll just go over the answer now. Um, okay, so I guess this example kind of I think it's a good example because you need to know like how winning strategies work to be able to answer the question. So like we're thinking about what is a winning strategy? Like a winning strategy means that no matter what white plays, black will always be able to win. Like that's what it means like for black to have a winning strategy. So what we're gonna do is we're gonna do something a little sneaky, right? Suppose that black has a winning strategy. We're gonna prove this by contradiction. We're gonna prove that this is not possible. How? Well, we'll show that if black has a winning strategy, then white must also have a winning strategy. Yeah, because double chess, you're allowed to move you're allowed to move a piece twice. We'll let white's first move be like knight f3, or moving the knight out and then moving a knight back in, right? Which resets the entire board, but the game is now passed to black, and the turn is now passed to black. And if you notice, it's the exact same setup as the original board, except now black is the one who's moving, not white. So in this sense, it's basically as if the game is reset, but black is the one who gets the starting move, and white is the one who gets the second move. But this is interesting because we said that black had a winning strategy. So, which implies that the player who goes second can always force a win. But in this situation, white is now the player that's going second, which implies that white can force a win. But that's impossible, clearly, because we said that black had a winning strategy. So we've arrived at a contradiction because we can't have both players having a winning strategy, which shows that black can't have a winning strategy. I mean, if we're just gonna boil this proof down to a single sentence, it's basically if black has a winning strategy, white can have a winning strategy, which is impossible. So yeah, so that kind of proves that black doesn't have a winning strategy. So either white always wins or it's a draw.
Okay, so should we move on to example two? Initially, there are 21 coins on a table. Chris and Ethan take turns to remove either one, two, or three coins per turn. The person who removes the last coin wins. Suppose Ethan goes first. Which player, if any, has a winning strategy? And I also want to say, with these combinatorial games questions, it can often be really helpful to just like play the game with yourself to like kind of get intuition about the question, you know? Yeah.
Okay. Um, I think I'll go with the answer now. Wait, if I guess I'll screen share from my tablet. Okay. So, well, one good thing to do with problems is start from, I guess, some simpler cases. So, in the problem, you start with 21 coins, but let's reduce that number down. Let's say if there's only one coin, who goes, who would win? Wait, does Ethan start first, by the way?
What would you say?
Does Ethan start first in the game?
Yeah, Ethan starts first.
Okay, right. If there was one coin, two coins, or three coins, clearly Ethan would win, right? So if it was n, so where n is the number of coins, right? We see that Ethan would win each time. So what happens if there's four coins on the table? Well, if Ethan goes first, he picks either one, two, or three coins, right? And then you're left with either, well, three, two, or one coins respectively. Then clearly Chris will win in this case. What happens is if there's five? Okay, okay, if there's five and Ethan goes first. Actually, so okay. Let me make a definition real quick. We'll call certain positions winning, like winning positions versus like losing positions, right? So a winning position, let's define it to be if you see this many coins on the table and it's your turn, you win. And a losing position is if you see this many coins on the table and it's your turn, you're screwed. You're done for. You lost, right? So one, two, and three are going to be winning positions because if you see one, two, or three coins on the table, you can just take all of them and you win. Four coins is a losing position. Sorry. Four coins is a losing position because no matter what move you do, one, two, or three, you're going to reduce it down to a winning position and give that to your opponent, and then they're going to win. So for five coins, is five coins winning or is it losing? Any thoughts? Yeah, yeah. So it's five. Five will be a winning position because you can take one coin and give it to your opponent, and you've given them a losing position. Now, if you take two or three and give it to your opponent, then you lose. But you're not going to do that because you're smart, right? And you don't want to give them a free win. So if you just strategically only take one coin when it's five, you have a winning position. Same with six and seven. If it's six coins, you'll take two coins and give your opponent a losing position. If it's seven, you'll take three coins and give your opponent a losing position. What happens if it's eight coins? Well, you can take either one, two, or three coins, which results in seven, six, or five coins, respectively, left on table. But all of those are we know are winning positions. We figure those out. So no matter what you do, you have to give your opponent a winning position. So eight would be losing. So from this, we see that if n is a multiple of four, it seems like it's always going to be lost. And we can see why, right? Because if it's not a multiple of four, you can simply like take either one, two, or three coins and make it a multiple of four. And if it is a multiple of four, you can't like you have to make it a multiple, a not multiple of four, which means you're from a winning position, you can make it a losing position. But from a losing position, you're always going to give your opponent a winning position. And the reason this works is because zero is a losing position by definition. If you're given a zero, that means your opponent has taken the last taken the last coin. So by using the strategy, which is always making it which is always making the number of coins a multiple of four, you guarantee a win because you guarantee at the end when you pass the last turn to your opponent, it's going to be a multiple of four, which means that you have taken the last coin. So if we describe a general strategy, to win, you always want to make the number of coins a multiple of four before giving the turn back to your opponent. So for example, with our original game, Ethan would the first move, Ethan would take this 21 and make it into a multiple of four. And then no matter what Chris does, let's say he, makes it 18, right? This is Ethan's turn. This is Chris's turn. Then Ethan can continue making it a multiple of 4. And at the end, let's say, Ethan will be the one to turn it into a 0, which means that he's taking the last coin, he's reducing the number of coins from 1 to 0, and he's won. So that's the general strategy, and it shows why Ethan can always win by following the strategy, which is just make it a multiple of 4. But the way we found the strategy is by considering winning and losing positions starting from the end, I guess, where n equals 0, and seeing which positions are winning, which positions are losing. Yeah, so that's often a good idea. Just look at small cases, play the game a little with small cases, and see who can force a win, who can't, who has to yeah, for what values of n can you force a win, and try to create an argument from that. Okay, so yeah, I think we can go move on to the next.
Do you guys need some time to like take that in, or can we just move on straight away? Okay, I'm gonna assume everyone understands everything. Okay, cool. Okay, we're gonna move on to invariance and monovariance now. So basically, an invariant is just something that always remains constant after every move. And then a monovariant is something that just either strictly like increases or decreases after every move. This might seem a little bit abstract, but they can help you solve problems when you have like, I guess like a game, well, not necessarily a combinatorial game, but just like any game with moves. And they want you to like the question asks you about like, I don't know, like some number of moves in the future. It can kind of give some insight into the game. So we'll just again just take a look at some few questions, see how we can use like invariance and monovariance in questions. So here's the first example. So consider a triangle with vertices at 0, 0, 0, 1, and 1, 0. In each move, we may take one of the vertices and move it along a line parallel to the other two vertices. Is it possible to have the vertices of the triangle be 1, 1, 3, 1, and 4, 2 after a finite number of moves? So yeah.
Okay, I think I'll go up the answer now. Okay, so what we're looking for here is an invariant, specifically like some property of the triangle which doesn't change no matter like how we apply these transformations. Okay, so here I have a triangle, and so like what our move consists of is we can bring our triangle and slide one of its vertices along this line, such that these two lines are parallel, right? So, something like these triangles are all examples of, triangles we could get by sliding along our original triangle along this line. Like, can someone like recognize like what is a property of all three of these triangles that stays constant, like as we slide it along this line? Yeah, okay, so Jackie got it. It's nice. Its area stays the same, right? Because if you look at all three of these triangles, they have a common base, and they have actually I'm gonna use a different color for this, but they have a base and they have a height, which is all the same. And obviously the area of a triangle is just half base times height. So these triangles all have the same height. I mean the same height, the same base. So they have the same area. So the area of our triangle is always going to stay constant. Um, but if you look at the original triangle, if you look at this area, okay, does someone tell me what does someone like figure out like the area of the original triangle compared to the final triangle? Yeah, they okay. The first has area 0.5 because it's half of like a 1 by 1 square, and the second one, if you I mean there are plenty of ways of doing it, but if you just do half base times height, you get area of 1, which is different from the original triangle. But we said that under these constraints, under these moves we can do, the area will always stay the same. So no, the first triangle can't like be transformed into the second triangle by sliding one of its vertices along a line parallel to one of its sides. Um, yeah, so I guess this shows how invariant is useful, right? It shows like a property of a system that never changes. So it kind of shows you, I guess, like limitations of like the system, right? This will never be able to turn into a triangle that's larger or smaller. Um, yeah, and once you have an invariant, a good thing to do is like I guess look at the initial condition or like, look at the initial like system and the things in it, and in the final one, and if there's something different in them, then obviously you're never gonna be able to get from the initial one to the final one. Okay, so I think we'll have to look at the next example now, which should be on a monovariant maybe.
Okay, example two. Um, a chocolate bar is made up of 420 small squares in a 6 by 70 grid. Ethan and Chris alternate moves in the following game. On their turn, a player must select a rectangle and cut it along a straight line into two smaller rectangles. None of the 420 smaller squares may be cut. The player with no legal moves loses. If Ethan goes first, determine which player has a winning strategy.
Okay, I'm seeing a few answers, so I think I'll go over the I'll go over how to do it now. Um, and the reason I'm going through it now is because I'm not actually sure about the answer. I mean, I suspect the answer is Ethan just because he wrote the question. Um, so I have a feel. I mean, he won the last game. Maybe he let me have this one. I'm not sure, but um, yeah. I guess we'll work through it together. I know how to solve it. I'm not sure about the actual answer. Also, Ethan, if you could mind letting me share my screen. Yeah, thank you. Okay, so okay, since I don't want to draw a 70 by or whatever chocolate bar, I'm just gonna draw a bit of a smaller one. Maybe we can make like 2 by 4. 2 by 5, why not? Okay, so let's look for something that I guess stays. Okay. Let's look at like a pattern once we start making some moves, right? So okay, I think Ethan went first. So okay, let's look at one possible move. Maybe he makes his cut, right here. Okay, I'm not gonna use straight lines anymore just because kind of golden. So okay, we turn one piece into two pieces. No surprises there. Let's say Chris makes his cut. I don't know. Sometimes when you get a game like this, you kind of just want to just play it a little bit. Just see what happens. Okay, so now we have some more pieces. Um, and let's make another cut here. And let's focus on the number of pieces. That's I guess that's like the quantity we're gonna be focusing on right now. So number of pieces. Well, we start off with one piece, and then after the first cut, we get two pieces, and then three pieces, and then four. Okay, I'll separate the different cuts. Line here, right? Okay, and I think this should make a bit of sense, right? I mean, after like each cut, you're only allowed to cut one piece, and you cut it strictly into two smaller pieces. So you're going to be you're turning one into two. So you're increasing the number of pieces by one each time. And this is a monovariant, right? It's something that increases, but it's something that constantly increases by one every time. Okay, so like I said, often when you have these invariants or like monovariants, it's good to look at the starting position and compare that with the ending position. So in the starting position, right, in the number of pieces we have, well, it's one. And in the final position, okay, well, since we have a simplified model here with only, 10 smaller pieces in a 2 by 5 bar, uh, in the real question with the 420 pieces, at the end, there should be 420 individual 1 by 1 like blocks. And at that point, you can't make any cuts. Because if there was any block that's larger than a 1 by 1, then someone could still make a move and increase the number of pieces by one. So you increase the pieces 1 by 1 until it is until you get to 420 1 by 1 pieces, and at that point you can't make a move anymore. Okay, so whose turn is it? So basically, no matter how you play the game, there's no strategy involved here. It's just you like one person is destined to win from the start because you're always going to make 419 moves before the game is finished and no one can make a move anymore. So this is an example of something where there's no real strategy. It's just and you notice that by noticing that the number of pieces increases by one every time, starting from one, ending at 420. and like nobody can like affect that. Like no amount of strategy you can do is going to affect the fact that the number of pieces strictly increases by one every move. Okay, so the first move is this is Ethan's move. This one is Chris's move. This one is Ethan's move. So going from odd to so eventually okay, so going from odd to even is Ethan's move. Going from even to odd is Chris's move. So clearly at the end here, since we're going from odd to even, this one is Ethan's move, which means that uh Chris doesn't have a move at the end and loses again. That's sly Ethan. Okay, so apparently Chris loses again. I mean, I guess next time you see a problem, maybe just say Ethan wins. Because I'm feeling like I'm seeing the pattern here. You know? Chris and Ethan play a game, Ethan wins. Yeah, okay. I guess we'll move on to the next one.
Okay, we're gonna move on to parity and coloring now. So we're gonna start off with parity. So when we talk about parity, parity just refers to whether like something is like just odd or even. It's a pretty basic concept, but it's like very, very common in Math Olympiad. It shows up all the time in both like combinatorics questions, even like number theory questions. Parity shows up a lot. I'm pretty sure our next example is not even like a game question. That's my bad. But like now parity is just very important, so that's why we put it in here, you know. So
By the way, no one said this lecture was going to be on games. I think
uh which I mean it's titled game theory in MINDNZ website, so like, you know. Okay, we'll just go on. Okay, so a set ABC of three positive integers is called addled if one of its elements is the sum of the other two. Does there exist a partition of the numbers 1, 2, all the way up to 2022 into only addled sets? And they have to be like distinct sets, so you can't have like the same number in two sets, you know.
Okay, I think I'll go I'll go down to now. So wait, we're even on the right slide? Okay, whatever.
Oh, my bad. Sorry about that.
Okay, okay, I hope everyone got the question. Okay, so we're gonna obviously use the idea of parity in our argument here. So we'll consider the parity of the elements in an added set. Okay, so we have three numbers in our set. Okay, what could they be? Well, I'll let E denote even here and then O denote odd. So they could be even, even, and even, right? Even plus even equals even. We have even plus odd gives us odd. Odd plus even is the same as even plus odd, and we have a final one, odd plus odd equals even. So notice how here that we have exactly two combinations for evens and odds in our sets. We can either have three evens or two odds and an even, right? Because there's only three possibilities for like evens and odds adding up to evens and odds. You can have even plus even plus odd equals odd, or odd plus odd equals even. So okay, so we have two options here: even, 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 or even, odd, odd. And now we're going to employ another parity. We're going to employ a parity argument to show that this is impossible, because we have our numbers from 1 up to 2022, and we need to partition them into these two types of sets, right? This even, 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 or even, odd, odd set. Now, I mean, there's a few arguments you can make, but the one I'm going to use is involves parity, and it's noticing that there's two odds in here, and zero odds. There's zero odds in the top in the first type of set, and there's two odds numbers in the second type of set, which means that in every set, the number of odds in it is going to be even. So you can like using these added sets, you can only you have to have an even number of odd numbers. Because if you had an odd number of odd numbers, you couldn't cleanly put them into added sets, because an added set can only take two odd numbers or zero odd numbers, right? So if I had some set of numbers one like 1, 2, 3, 4, 5, and then let's say 8. Well, actually, well, 8. Why not 8? Just do 6, okay? Right? Then okay, could you partition this into two added sets? Well, by logic, you could not, because there are three odd numbers. So you could have two of these odd numbers in one added set. For example, 1, 3, 4. That's bringing the 1 and 3 into an added set. But you wouldn't be able to fit the 5 anywhere, because the 5 needs another odd number to pair with it to make an added set. Okay, so now let's consider how many odd numbers are in this set. Well, exactly half the numbers in here are going to be even, and half the numbers are going to be odd, right? Because it goes, odd, even, odd, even, odd, even. So the total number of odd numbers is just 2022 divided by 2, which is equal to 1011. Which, and we just shown if there's an odd number of odd numbers, you're not going to be able to partition them into added sets. So we've shown that it is in fact not possible to partition the numbers 1 2022 into an added set. And okay, that's a nice parity argument where yeah, where we show, a parity. We need the parity to be either even or odd, but we show that the actual parity is the other one, and therefore it isn't possible.
Okay, we're gonna move on to coloring now. So this might sound a little bit weird, but like when you color in grids in math, it can actually sometimes make the questions easier. And that might be a bit hard to believe, but we will look at some examples. But like the most common types of coloring you'll see in Math Olympiad is like if you have a grid, you color every alternating square black and white, and you find a relationship between the colored squares that can help you like get some insight into the problem. So we will look at a very famous example question. I'm pretty sure everyone who has done Olympiad math has seen this question before. Consider an 8 by 8 grid with the top left and bottom right squares removed. Is it possible to completely tile this grid with 1 by 2 dominoes without overlap?
Okay, I've seen a few answers, so I guess I'll go ahead and go with the answer now. So, okay, what we're gonna employ is we're gonna employ like a pretty famous coloring, maybe perhaps the most used coloring. Um, it's gonna be a checkerboard coloring. So, like it's like I guess a pattern you see on a checkerboard or a chessboard. It's just black, white, alternating. There's other types of colorings as well, but this one, I mean, it's one that works here, right? So sometimes you might want to have to try a few different colorings before you find one that works. So it's gonna look something a little like this. We have you see we have our top left and our bottom right corners removed, and then this right here is a 1 by 2 domino. So what we're gonna notice is that like as you place, what we're gonna like look for is the colors that the domino lies on when it gets placed. So I think it's pretty clear that anywhere you orient it, it's gonna cover both exactly one white square and one black square, and that's kind of just because like in a checkerboard coloring, every black square borders a white square, every white square borders a black square. So if you pick two adjacent squares, they're going to be opposite colors. So no matter how we place these dominoes, the number of black squares they cover and the number of white squares they cover will always be equal, right? Another way you could think of this is you can think of the quantity black squares covered minus white squares covered, and this is an invariant. It's always going to equal zero. So okay, let's look at the starting position and the desired final position. So the starting position, how many black squares and how many white squares are there? Well, one way you could do it is you could just count every black square and every white square. A smart, like I guess a more efficient way is thinking about the entire. Pretend that the corners weren't removed. If you just look at an 8x8 like chessboard, there are, well, 8x8, there's 64 tiles in total, and by symmetry, the number of black tiles equals the number of white tiles. So there'll be 32 black tiles, 32 white tiles in a normal, like in a normal 8x8 grid. But because we've removed these two corners, these two should be white. They would normally be white. So, but we've removed them. So from 32 white and 32 black, we have turned into 32 black and only 30 white tiles. So we said that a domino can cover exactly one black square and one white square, which means that the number of black squares and white squares covered must be the same. But in the final position, if we've covered every single square with dominoes, that means we've tiled 32 black squares and 30 white squares, which contradicts our initial, which contradicts the idea that the black squares tiled must equal to the white squares tiled. Another way you can look at it, like using the invariant idea, is because we said that the black squares minus the white squares is invariant, it's always equal to zero. In the final position, we would have 32 minus 30 is equal to 2, which is not zero, which means it is impossible to reach reach the final state. Some other examples of colorings, by the way, just to give you guys an idea of maybe something you could like try is oh something like if you have a board, you could try coloring alternating columns like this. You could also try something like coloring in. I mean, if these are your grids, you can try coloring in like 2x2 grids instead of just one, like a 2x2 checkerboard like this, instead of just 1x1. Um, Perhaps you could do something like coloring in only like one out of these four. So it's like checkerboard, but it's like expand. It's like the black is like more sparse. Or you could try. You don't need just two colors, and black and white doesn't really matter. You could use a third color, something like black, then white, then yellow, 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 and then black, black, like this again, and then white, 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 something like this. You could use 3 colors. You could use four colors. You could use 5 colors, right? You could use as many colors as you want. It's just like as long as it works, right? As long as it helps you solve the problem. But most common is probably gonna be like 2 colors, and either checkerboard or one of these more common things. Sometimes you have to get a little creative, but yeah. And obviously, it's not always going to be like square grids that you're coloring. Sometimes, you have other shapes that you want to be coloring. But yeah, just if you want to show something's impossible, like coloring is like it's not obvious. It's not an obvious way of showing it, but it's good to keep in mind. Okay, I think that yeah, that's about time, right? 9 p.m. now.
We still have one more question though. If anyone wants to stay and just
We have another
try
question.
that question. Yeah, we have two more questions
Okay,
actually.
yeah, no, but that's if we had too much time. Okay, whatever. Okay, do you want to go to?
Does anyone want to stay for the last question?
Okay, Jackie will say.
Oh, we got two people that wants to stay. Let's go. Oh yeah, this is a question right here. So there are 10 blue, 15 red, and 20 yellow chameleons. If two chameleons of different colors meet, they both simultaneously change to the third color. Is it possible for all the chameleons to be the same color? And this
Um,
is just like a miscellaneous question. Like it's not
yeah,
necessarily like coloring and stuff. It's one of
um,
the techniques we've talked about already.
yeah. I guess I might give like a little bit of a hint in like a few minutes. Just you know.
Uh,
Oh, so are you even sharing the screen? Sorry.
was I not sharing my screen the entire time? Oh, that's crazy.
Yeah, it is crazy.
I just put it up. There we go.
Okay. Yeah, here's the question. Okay, well, I'll just say something. I think it is. I don't even remember the solution to this question. It should be some sort of like an invariant, but it's not. It's okay. I'll give a bit of a bigger hint just because like I don't want to sit here and just like give the answers, right? I want to you guys have a chance to solve the questions. Um, consider. I hope you guys remember your number theory lessons. Consider mod three. I mean, more specifically, maybe just yeah, maybe try do like a few moves and then look at like look at the numbers of the different colors mod three and see if you notice something. Wait, numbers? Well, no, something mod three at least. I'm trying not to like say everything. Yeah, I'm not sure how much time I'm meant to be giving because I guess the lesson's over now, so there's no real time constraint here. But yeah. I might give a bit of a bigger hint now. Maybe consider consider the differences between in the numbers between two colors. Yeah, I think I'll go with the answer in a minute. Okay, I think I'll just go with answer now. So we're gonna be looking for so okay, we're gonna be looking at the numbers. We're gonna be looking at the difference between the numbers, right? Let's just take the chameleons, the number of chameleons that are blue and red. So right now the difference is 5, right? 15 minus 10 is 5. Okay, let's make some moves. We have three possible moves, right? Either okay, case one is two blues turn into oh sorry, a blue and a red turn into two yellows. You get 9, 14, and 22. So that's one possible move, right? In this case, we get 14 minus 9 is still 5. Well, that makes sense, right? We removed one from blue and we removed one from red. So it should make sense that the difference between them stays the same. Okay, what's another move we could make? Well, a blue and a yellow make two reds. This is an example of the second type of move. And now the difference is 8. Okay, that's interesting. The difference has increased. So the difference isn't invariant. It does change. Okay, what if two what if a red and a yellow make two blues? That's our last type of move. Okay, well we're back to 1510 now, and it's back to 5. Okay. So remember when I said we want to be considering stuff mod 3. Oh god, that's a really large eraser. Well, if we keep playing this game a little bit, right? If we just make random moves, random moves, random moves, we and we look at the difference between blue and red and blue. Well, I'm not gonna sit here and simulate a bunch of random moves, but maybe it looks something like this, right? Maybe if you keep going, you're gonna get 5, 5, 3, 5, 3, 3, 5, 8, 13, something like this. And what you might notice is 3. Oh god, I've you know, brain not good. Okay, so it should be 2. And I don't know why I put 13 here. Yeah, apparently not very smart. Okay, there we go, right? And if you look at it, you'll notice it's minus 3 plus 3 minus 3 plus 3 plus 3 plus 3, right? And here it's plus 0 plus 3 minus 3. Okay, so it looks like it either stays the same, increases by 3, or decreases by 3. And let's look at the moves individually to see why this would be. Okay, move 1. Between blue and red, they both lost 1. I mean, they both lost 1. So the difference should overall it should be plus 0. Right. Move 2. Well, blue decreases by 1 and red increases by 2. Overall, their difference is plus 3. And blue, move 3, blue increases by 2, red decreases by 1. So overall, it's minus 3. And only, okay, it's only minus 3 or plus 3 because blue is less than red. It doesn't really, the signs here don't really matter. What matters is that it's, it's changing by 3, right? After every move, it either changes by 0 or it changes by 3, which means that we arrive at the conclusion that this value, this value, this like 5, 5, 8, this thing is not invariant. It does change, but it is an invariant mod 3. So this thing will never change mod 3. Okay, so now that we found our invariant, I'll write it down real quick. There's something special about, blue and red. We could have done this with red, yellow, or blue, yellow, but it doesn't really matter. The difference between two colors is invariant mod 3. So now let's look at our initial and our final conditions, right? Initially, the difference is 2 mod 3, right? Since we have 5, 8, 2, these are all 2 mod 3. But if you look at the final state, we want all 3 of them to have the same number of colors, which means that the difference between them must be 0, which is 0 mod 3. Um, so obviously because the difference must stay the same mod 3, it must always be 2 mod 3. That means we can't get from the initial to the final condition, which shows it's not possible. And a lot of times for these games, it will just be like you find some kind of variant, some kind of like reason why it can't. Um, like I like why you can't get to like the final condition. Sometimes you can, and in that case, you have to find some kind of construction, right? And normally it won't be an easy one, but you have to kind of outline some kind of like way of some kind of way of getting there. But yeah, okay. Okay, I think that's about it, huh? So yeah, you guys can leave now. Yeah, see ya.
Do you guys have any questions or not? Ooh, wait, Chris.
Mhm.
Wait, you're recording, right?
Yeah. Well,
I, I thought I was supposed to be recording, so I was like, oh, I wasn't recording the entire time. Whoops.
actually, I don't know how the recording thing works, which is a bit suspicious.
Yeah, do you have any questions or not? Are you even there? Is this person AFK?
Nah, clearly not. Clearly not.
What do you mean clearly not? I haven't said anything yet. Uh, well, let's just chill here together then. Boom, 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 boom,
Oh,
boom. Bro, they left, bro.
yeah.
No.
Come.
Bro, they pulled up the thumbs up and then they left, man.